So the last application that the authors of this section walk us through is a probability application. And it's here where the sort of the worlds of physics and the worlds of chance kind of collide with one another, because in physics, when we have a density function, we're talking about the mass of something per unit area or per unit volume. And in probability, we can think of a probability density as being a probability per unit area or probability per unit volume, or even a probability per unit of length, as a function that sort of describes which outcomes in a sample space, which values of a random variable are more likely or less likely to occur than others. So where probability density is high, we have a high chance of a random variable taking values in that location, and where the probability density function is small, then it's not as likely to find that random variable in that at having that value. And so in probability theory, one of those density functions can tell us, for a continuous random variable, what is the probability that that variable's value is in between two limits. And if that works that way for a single random variable, then it can also work that way for two random variables that vary jointly. So if I have a joint probability density that tells me where x and y are more or less likely to be found, then that can serve just like a density function does when we're talking about physics problems. And if I can compute the correlating quantity to mass in this example would then be the probability that x and y reside within that region in the xy plane that we're interested in. And so the only additional stipulation when we have a density function that we want to be a probability density function, the last stipulation that we have is that the total amount of probability, the probability that x and y are anywhere at all on the entire region, has to add up to equal 100%. Right? So that's the one extra caveat that we have to have for a function to be a probability density function, is that its total integral has to add up to 100%. It has to add up to 1. But beyond that, every other kind of integral that we could do then tells me what proportion of that total probability is consumed within the region over which we're integrating, right? Because we don't have to divide by the total mass anymore to find proportion, because the total mass is equal to 1. And so just taking the integral of a probability density over a region in space is going to show me the probability that x and y are within that region inside of space. So the example that they walk us through here is you're manufacturing smoke detectors, and you get these components, these two different components from two different suppliers, and the lifespan, each of these components wears out after a certain number of years. One component wears out after X years, and the other component wears out after Y years. And we know how each of those lifespan numbers is distributed according to an exponential distribution. And so the joint probability density for them both wearing out is given by this product of these two functions, e to the minus x, e to the minus y. And so you can show that the integral over the entirety of the sample space, which is x ranging from 0 to infinity and y ranging from 0 to infinity, that total integral is equal to 100%. So that's just a straightforward improper integral verification. That's down here. And so this gets to be a probability density because its total integral is equal to 100%, equal to 1. And so then the question is, what are the odds that the smoke detector will fail within 1 year? In other words, what are the odds that both of my x and y have a value between 0 and 1? And so you'd be integrating this probability density over the square, 0 to 1 in the x-axis and 0 to 1 in the y-axis. And then that number is going to give us the probability, and so forth. The only other interesting part of this question is that they have you in part D look at a slightly different probability density that has an e to the minus 2y in here. So maybe one of the components has a longer average lifespan than the other. And so in order to turn that into a probability density, we need to choose a constant k. We need to multiply it by a constant k that makes the total volume, the total probability, equal to 100%. It's called normalizing a density function. And so to do that, we just find the integral with that k constant in place, and then just set the result equal to 1 and use that to solve for k. So when I evaluate this double integral, k e to the minus x, e to the minus 2y, the double integral evaluates to 1/2 k. And so in order to normalize this probability density, k needs to be 1 divided by 1/2, or k needs to be 2. Right? You're welcome to do parts B and C if you'd like to during the week, just to get some additional practice applying double integrals to the situation of probability. If you're a math major at Bridgewater, probability theory is one of our more popular upper level courses. It's a 400 level course for us, and this is part of what you do in that 400 level probability course, is figure out how calculus can help us to assess probabilities of random variables, continuous random variables, both individually for single variable calculus and also jointly if they vary jointly using multivariable calculus.